So yesterday we studied two laws, Ampere's law and Faraday's law, and apart from that we also studied continuity equation. So again so far we have studied four laws apart from continuity equation. So again for brevity I'll mention them. So there are two forms. What are they? Integral form and point form. And the first law we studied was what? Gauss law for electric fields. So what was Gauss law for electric fields? Closed surface integral of d vector dot ds vector equal to q enclosed. And what was the point form? Del dot d vector equal to rho v. Right? Then we studied Gauss law for magnetic fields. What was it? Closed surface integral of b vector dot ds vector equal to 0. So its point form, by applying which theorem? Divergence theorem was del dot b vector is 0. Then we had Ampere's law, abbreviated as AL. So what was it? Closed line integral of h vector dot dl vector. We can say contour integral. What is a contour integral? That the traversing can be independent of the path. So it should be what? I enclosed. Right? And it can be written as surface integral of j vector dot ds vector. And what is the point form? Del cross h vector equal to j vector. Then finally we have Faraday's law. What is Faraday's law? Closed line integral of E vector dot dl vector equal to minus deba by deba t surface integral of b vector dot ds vector. And what is the point form? Del cross E vector equal to minus deba by deba t b vector. So this is the four laws we studied. Gauss law. There are two forms, electric field and magnetic field. Then we have Ampere's law and Faraday's law. Then we went to the next topic, which was continuity equation. Now it can also be termed as inconsistency in Ampere's law. Now why it is, that we'll see in some time. And that inconsistency leads to nothing but continuity equation. So what was continuity equation? We have already derived it. It is del dot j vector equal to minus deba by deba t rho v. And how we arrived at this equation? We said consider an arbitrary surface ds having initially which is charged up. So it has a charge q. So we said I equal to minus dq by dt. Why we said minus? Because as the time passes, the charge is decreasing with respect to time. Then we said I is surface integral of j vector dot ds vector minus d by dt volume integral of rho v dv. So we d by dt we converted to deba by deba t. Why? Because we said dv is now dx dy dz. So it is dependent on three variables. So that's why it becomes what? Deba by deba t. That is partial derivative. So now this is surface integral, this is volume integral. So what we do? We apply divergence theorem. So we get volume integral, and when we solve, we get this equation. Then what we said, for static fields, it is not dependent on time. So del dot j vector equal to 0. Right? And we said this is nothing but KCL equation. Divergence of current density is 0, indicates it is KCL. So from that we said for Faraday's law it is what? KVL. So Faraday's law indicates in static form, obviously indicates KVL. So this is what we discussed yesterday. So now let's go further. So what we would like to say is, let's start with Ampere's law. Why we'll come to know in some time. So Ampere's law, and let's take point form. So in point form, so what is it? Del cross h vector equal to j vector, right? So let's take divergence on both sides. So taking divergence on both sides, what we get? Del dot del cross h vector equal to del dot j vector. So divergence of a curl equal to divergence of j vector. Now it is a standard mathematical identity that divergence of a curl is always 0. So I can say del dot j vector is 0. So therefore del dot j vector equal to 0. Right? So this is what we get. So let's say this is equation number 1 and this is equation number 2. So what we observe, this is del dot j vector, this is also del dot j vector, and we have assumed Ampere's law in point form, so it is time varying only. So this is also time varying, but both are not equal. So 1 is not equal to 2. So there is some problem. So what is the problem? So it means that, so let's see what is the problem, whether the problem is here or whether the problem is in Ampere's law. So when we come here, we see that all the assumptions are correct. So this equation has to be correct. So that is continuity equation is correct. Means the problem has to be in Ampere's law. So remember, we are not saying that Ampere was wrong. We are just saying that Ampere has not considered some cases, or it is a special case. So he has not considered all the cases or all the conditions. So that is why we are not arriving at the correct equation. So let's see what Ampere has missed. So for that, what we do, we assume an arbitrary vector as G vector. We write, to resolve this issue, we'll assume an arbitrary G vector. So to resolve this issue, we assume an arbitrary G vector such that so we are getting the problem in Ampere's law, so we'll assume it here. So is that del cross H vector equal to G vector plus G vector. Now again take divergence on both sides, so we'll get del cross H vector equal to, what will this be, del dot J vector plus del dot G vector. Now divergence of a curl is 0, so this will be 0. Now what is del dot J vector? It is, so we'll keep it like this only for the time being, plus del dot G vector. So therefore del dot G vector equal to minus del dot J vector. And what is del dot J vector? Minus dabba by dabba t rho v. So minus minus will become plus. So this is dabba by dabba t rho v. Then rho v is what? From point form of Gauss law we can write. So from point form of Gauss law for electric field, del dot G vector equal to dabba by dabba t del dot D vector. If you have a doubt, just now we have written at the start of the lecture, del dot D vector is rho v. So I have used the inverse substitution, rho v is del dot D vector. So therefore, can I say G vector is what? Dabba by dabba t D vector. Right? So this is what Ampere had missed. Again, we are not saying Ampere was wrong. We are just saying that Ampere has missed one special condition or special case. So that is this case. And who did this? It was done by the very famous but very less known scientist James Clerk Maxwell. So you might have studied Maxwell's equations in physics in 12th standard, or maybe in applied physics also, first year. So that is what we are going towards now. So we'll study them in detail. I don't know how much you might have understood. So you can definitely understand it. So this is what, so this G vector is what? This vector. So what we have to do, we have to just modify the Ampere's law. And again, who did this? It was done by Ampere. So these are our original equations. So this is having some problem. So we'll discard this. So instead of Ampere's law, now it becomes what? Modified. So I'll write M. So it indicates what? Modified Ampere's law. So closed contour integral of H vector dot dl vector equal to I enclosed equal to surface integral of J vector is replaced by what? J vector plus G vector. So J is, and G is what? Dabba by dabba t D vector. So J vector plus dabba by dabba t D vector dot ds vector. And what will point form become? Del cross H vector equal to J vector plus dabba by dabba t D vector. Now the question is, what is this dabba by dabba t D vector? Now we already know this is what? Current density, and this is due to current. So it, strictly speaking, it is conduction current density. So what it should be? This should also be a current density. So this is also a current density, because both the units should be satisfied. So now this is due to what? Conduction. So this has to be due to what? Dielectric. So this is dielectric current density. Means current can also flow in the dielectric. That is what was proved by Maxwell. and that is why these equations together are called as what? Maxwell's equations. So for brevity, I will again write it. So we have arrived the crux of the course, which is Maxwell's equations, and they are for time varying fields only. So first we studied for Gauss law for electric field, and first is integral form, second is point form. So what was Gauss law for electric field? Closed surface integral of d vector dot ds vector equal to q enclosed. And what was the point form? Del dot d vector equal to rho v. Then we went to Gauss law for magnetic fields. Closed surface integral of b vector dot ds vector equal to 0. What is point form? Del dot b vector equal to 0. Then our Ampere's law is now modified, so it is modified Ampere's law. What is it? Closed contour integral of h vector dot dl vector equal to I enclosed. If you want, you can skip that. You can directly write surface integral of j vector plus dabba by dabba t d vector dot ds vector. So in point form, it is del cross h vector equal to j vector plus dabba by dabba t d vector, right? Then finally we have Faraday's law. So Faraday's law is closed line integral of e vector dot dl vector equal to minus dabba by dabba t surface integral of b vector dot ds vector. So in point form, what is it? Del cross e vector equal to minus dabba by dabba t b vector, right? So these are what Maxwell's equations in integral and point form for time varying fields. So let's try to understand the equations in equations one by one. So we already have studied first two, what they mean. What they mean in the sense, what we are not understanding, we are not directly biating the equations. We want to see what the equations are saying. So that is why then only you will feel the equations as beautiful, when you understand what is the equation saying. So what is the first equation saying? We already know this. The total amount of electric flux density coming out of a surface is always equal to the electric charge enclosed by the same surface. So that is what first equation says. So this equation should also say the same, because it is derived from this only. So it is called as point form. Why is it called as integral form? Because we see integrals here. Now why we require point form? Now this we are talking about what? Electromagnetic waves, so which will come further in due course of the lecture. So for example, you take a room, you want to solve Maxwell's equations in a room, so we need to solve it here at each and every point. So that is where these equations will be used. So now why we may want to solve Maxwell's equations in a room is, for example, we want to check how much electric field is coming towards the mobile from the mobile tower. So for that we can use this point form. So Gauss law for magnetic fields. Then we said, if we are considering a magnet, if we break into two, what is happening? We are not able to separate the north and south poles. So we cannot have a single magnetic monopole. So that is why this charge becomes, magnetic charge becomes 0. So that is indicated by what? The total amount of magnetic flux density B vector coming out of the surface is always equal to 0. And this is the point form, right? Now these are what? So we know, let's see Faraday's law first, because everyone, you know it from your childhood. So what does Faraday's law say? Whenever there is a change in magnetic field, we'll always have a EMF induced. So let's see where we are getting the change in magnetic field. So this is the magnetic field. Is there is a change in magnetic field? Yes. How? Because we have dabba by dabba t. So there is a change with respect to time. So there is a change with respect to time, as the statement says. And what it is equal to? It is equal to E vector dot dl vector. Means whenever there is a change in magnetic field, I will have the E vector dot dl vector, that is voltage. Why? Because E is V by D. So this is understanding from your old point of view. But what does electromagnetics tell us apart from this is, whenever I have a changing magnetic field with respect to time, I will always have an associated electric field. So that is what this says. Now let's come here. So this is also says the same. Whenever I have a magnetic field, I'll always have an corresponding electric field. But usually we try to understand from this. Now let's come to modified Ampere's law. Now what is this D vector? Now what I can write D vector as D vector. I don't know. I don't remember whether I have given these equations. So there are two further equations. D vector is epsilon E vector, and B vector is mu H vector. Right? Then I have already told epsilon is epsilon 0, epsilon r, mu is mu 0, mu r. Right? So for that you can see the previous videos. So D is epsilon E vector. So I can write this is epsilon E vector. So what I am getting? Changing electric field. Why changing? Because this is with respect to time. So as time changes, the electric field will change. So whenever I have a changing electric field, what will I have? I'll always have a corresponding magnetic field. Right? Means if this field is 0, this will also become 0. Assuming J vector is 0. Then when I have B vector is 0, that is right hand side is 0, what will happen? The electric field also be 0. So what we understand, whenever there is a changing magnetic field, I'll always have an associated electric field. Then what I am saying, whenever I have a changing electric field, I'll always have an associated magnetic field. Means E cannot exist without H and H cannot exist without E. So that is what we are seeing. So this is the first takeaway from Maxwell's equations. Fine. Next, now I said this term is 0. Assume. Means if this term is not there, electric field also will not be there. So let's see that case. So that is the case when time, it is not time varying. So time, it is not time varying indicates it is static. So next we write Maxwell's equations for static fields. So Maxwell's equations for static fields. So again, integral form, point form. So we have Gauss law for electric field. What is it? Closed integral of d vector dot ds vector is Q enclosed. I am purposely again writing the equations, or I am writing the equations again and again so that you are conversant with them. And this is a very important question. It is a question, derive the Maxwell's equations in integral and point form. It has been repeated in almost each and every exam for 10 marks. So they are very important. That's why I am stretching on this and writing them again and again. Then we have modified Ampere's law. What is it? Closed contour integral of H vector dot dl vector equal to surface integral of J vector plus dabba by dabba t d vector dot ds vector. So this is del cross H vector equal to J vector plus dabba by dabba t d vector. Then we have what? Faraday's law. So Faraday's law is closed integral of E vector dot dl vector equal to minus dabba by dabba t surface integral of V vector dot ds vector. We have del cross E vector equal to minus dabba by dabba t B vector. So these are the Maxwell's. Oh, I made a mistake. I have to write for static fields. So they should not be dependent on time. Right? So this equation is correct. This equation is correct for static fields. For static fields means what? They are not dependent on time. Means dabba by dabba t term should not be there. So this term goes away. So you have just what? Closed contour integral of H vector dot dl vector is surface integral of J vector dot ds vector. So if you observe, it is the same as the equation we crossed out here. Closed contour integral of H vector dot dl vector is surface integral of J vector dot ds vector. So what we were saying, that's what I was stressing. Ampere was not wrong. He had not considered a special case. So that special case was what? Adding this term. So that term was added here. So that's why this Ampere's law became modified Ampere's law. So again this term will not be there. So again closed integral of E vector dot dl vector, this is dabba by dabba t. So this entire term will go away. So this will be what? 0. Similarly this will be 0. Right? So that is what I was saying. If there is no magnetic field, I will not have an electric field. and vice versa. Okay. So again, this is very important. Almost every exam they have asked for 10 marks. This along with derivation. So I have also taken the derivations for each and every law. Gauss law for electric, magnetic. This is not a derivation as such. This is concept. So that you have to write. Then this is modified Ampere's law, again derived, and Faraday's law also we have derived from E equal to minus d phi by dt. So next, what we understand from Maxwell's equations, that will note down. That is, we'll note down the significance of Maxwell's equations. So the question is usually in this way: derive the Maxwell's equations in integral and point form and state the significance. So next is significance of Maxwell's equations. So first thing is, what we have known, that electric fields and magnetic fields are always dependent on each other. So first takeaway is interdependence of electric and magnetic fields. Next, Maxwell's equations also tell that there is the existence of electromagnetic, abbreviated as EM wave. So how this happens, that will prove in due course of the lectures. So finite speed of third is finite speed of propagation of EM wave. So EMW I can read. So I'll also prove that from Maxwell's equations we get the EM wave has a finite speed. That is, it is not traveling at infinite speed. And finally we see for free space propagation, or free space propagation is at the speed of light, and light itself is an electromagnetic wave. So these are the four takeaways from Maxwell's equations. From this, what we have proved, we have already proved this one, so let's put a tick mark there. So in due course of the lectures, I'll prove the point number 2, 3 and 4 as well. Okay, so I'll keep this sheet as it is. So as and when I prove, I'll come to this sheet and put a tick marks. Okay, so these are nothing but your Maxwell's equations. Okay, so make sure you write them. Even if you miss this dot, you will be defying the laws of physics. So these dots are very important. So even if you miss these dots or some vectors, then you might lose marks if the examiner is very strict. So make sure you write them and practice them. Okay.